Hello, and welcome to the first video in a short series on the development of the theory of acids and bases. In this video, we'll go and look at the historical background of how the current theories were developed and where they came from. Early on, from the beginning of time, people obviously noted that some things tasted sour, while other things they encountered in nature were both bitter and slippery to the touch. It was also noted that if one looked at plants, depending on the soil that they were planted in, if the soil was, for want of a better word, sour, the leaves would turn from blue to red. On the other hand, if the soil had a bitter and slippery consistency, the leaves on the plants would change from red to blue. Eventually, the material that caused this change to happen in plants was isolated, and it was named litmus. So very early on, the definition of acids and bases was as followed. An acid is anything that turns blue litmus red, and a base is anything that turns red litmus blue. Moving on, the etymology for the words acid and base goes back way further than the understanding. Starting in ancient Greece, they obviously were observant and realized that some foods were very sour and did not taste good at all. The Greek word for sour was xenos, which literally translates to sour. As time went by, the Romans borrowed heavily from the Greeks. The Romans noticed sometimes their favorite drink, wine, went bad. They took xenos and turned it to acidum, also meaning sour. However, the Romans were also creative. They soon figured out that the sour wine could make their salads taste better, which is why acidum is actually the Latin word for vinegar. It is also the root for the modern word acid. Moving forward a couple hundred years to the Middle East, people would mix together ramad, or ash, add some ma'ah, or water, and top it off with some hajar alkals, or limestone. The purpose for doing this was to make something, again, very useful, because if you heated that mixture up, you wound up making soap. Additionally, hajar alkaz is the root for the word alkaline, which is generally used to describe anything basic. Eventually, scientific method took hold, and the theory of electrolytes was developed. Electrolytes, very simply, are solutions that conduct charge. In order to conduct charge, they must contain charged particles, so the solute must be ionic. A scientist named Svante Arrhenius was the first one to look into this phenomenon. He examined it very closely and noticed some things, that some of the electrolytes he looked at turned blue litmus red. Those contained H+. Things that turned red litmus blue contained OH-, and other electrolytes did not change the color of litmus at all. Arrhenius concluded that anything that turned the litmus red was an acid, an electrolyte that donates H+ to solution. Things that turned litmus blue were bases, or electrolytes that donated hydroxides, OH- to solution. And things that did absolutely nothing to the litmus were simply salts. They were neither acids nor bases. Going further, Arrhenius also started to look at solubility. He did this by investigating something called conductivity. Okay? The conductivity of a material, or the conductance, measures how much charge that material can carry. Essentially, it's related to the concentration of the solution, and the conductivity of any given solution is intrinsic. So, the common belief was that some electrolytes very simply dissolved completely in water and were completely soluble, while other electrolytes would simply not dissolve in water and were insoluble. Looking at the conductance of these different solutions, Arrhenius expected that given an ideal conductivity where all of the ions dissolve, the ratio between the measured conductivity and the ideal conductivity would be 0 for an insoluble solution since no ions were present. And for a completely soluble solution, that ratio would be 1 since all of the ions dissolved. That would give you the maximum conductivity. His expectations were met for completely insoluble solutions. However, for things that seemed to dissolve, he did not get the expected result. Instead, what he found out was that some solutions had a ratio of 1, which was unexpected, but other solutions had a ratio of less than 1. This could only mean one thing. In the solutions with a ratio of 1, which he called strong electrolytes, all of the ions possible dissolved. Everything was 100% soluble. In the solutions where the result was less than 1, the only reason where that could happen is if those salts were not completely dissolved, but were only partially soluble. And Arrhenius jumped to the conclusion that these had to have existed in equilibrium. Now, Arrhenius went further with his theory of electrolytes. He said acids donate H+, bases donate OH-, and all this happens in solutions of water. Salts, he reasoned, were chemically inert. Additionally, his theory holds that electrolytes can either be strong or weak, where strong dissociates completely in water. And in this, there are very few examples of strong acids. There are only 6: HCl, HBr, HI, nitric, perchloric, and sulfuric acids are the only 6 strong acids that dissociate completely in water. Additionally, there were very few strong bases. The strong bases were lithium, sodium, potassium, rubidium, and cesium hydroxides, essentially all of the group 1 hydroxides. And in addition, strontium hydroxide and barium hydroxide from group 2. Everything else that was not one of these 6 strong acids or 7 strong bases was considered weak and existed in equilibrium in solution. In future videos in this series, linked in the description below, we will see how this theory has been evolving throughout the years and where it stands now and how to use it. From this, it's important to realize that for the purposes of the discussion of acids and bases, 1, they only act as acids and bases when they are dissolved in water. And 2, the lists of strong acids and strong bases has not changed. There aren't that many of them, so if you are working in the field of chemistry, or studying chemistry, it is good to remember what these are. Thank you very much, and I hope you enjoyed this video.